Hello and welcome to today's video lesson where we're going to cover how to calculate the pH of a weak base. So let's say I have a 0.100 mole per liter solution of N2H4, that's a weak base. What is the pH value of that solution? So the Kb of the base is also given to me, which I will need to solve the question. So typically to solve for the pH, I need to use my pH formula, which is pH equals negative log of the H3O concentration. So what we're going to see is we're not going to actually make H3O directly in this equation. So for example, let's take our weak base N2H4 and let's write a dissociation equation for this. Now it's aqueous, so I'll react it with water. Now I'm going to put it in equilibrium because it's a weak base, so it's not going to fully dissociate. So we're going to use a Bronsted-Lowry definition of acids and bases. So because this is a weak base, its definition is that it will be a hydrogen ion acceptor. So hydrogen ion H+ will come from water, and it will be accepted by N2H4 that will create N2H5+. And this is called my conjugate acid, by the way. Now, because the water gave away a hydrogen ion, the water will become, I'll put AQ here, the water will become OH negative. That's my conjugate base. Okay, so notice in my dissociation equation, I don't have hydronium. Hydronium is H3O, so I don't have that anywhere in my products, but I do have hydroxide. So I'm going to actually solve for the POH in this question, and then we're going to convert it to pH using this expression. So we're kind of doing an extra step in a weak base problem, but it's very similar to calculating the pH of a weak acid. So we are going to have to set up an ice table or ice box, which stands for initial, change, and equilibrium. So the initial amount of the weak base I have is 0.100 m or moles per liter. The water we're going to omit because it has a constant concentration. The conjugate acid and then the OH minus, its initial concentrations are 0. So products, they start at 0 and they increase over time, right? They increase as the reaction goes on. So this, by the way, this is a 1:1:1:1 mole ratio. So my reactants, when they change, they will decrease by their mole ratio. So in this case, it'll decrease by 1x or just x. The products, again, it's 1:1 ratio. They will increase by x, which means at equilibrium, I'm going to have 0 plus x or just x of products. So remember, that's what I want to solve for this because that will tell me how much hydroxide do I have. And once I know that, I can solve for the POH. Now for the reactant, I'm going to use a little bit of a math shortcut. That's called approximation. So we're going to say here, we're going to approximate, use approximation. We're going to say that X on the reactant side equals 0. Because that's a fair assumption when I'm dealing with weak acids and weak bases, because by definition, weak acids and bases, they dissociate very, very little. So that means this initial amount that I have, it barely breaks down. And that also means I'm going to have very little product produced as well. So we are going to make an assumption that X is 0 on the left side, which means at equilibrium, my weak base concentration will be very close to 0.100 moles per liter. Okay, now you don't have to do approximation if you want. It will just be a lot more math, but I'm going to just save some time by using approximation here. Okay, so how do I solve for X? So here's one more clue in the question. Kb is given to me. So if you guys remember, every equilibrium constant, this is the base equilibrium constant, it will always be the ratio of your products to reactants. So I know that Kb will equal concentration of N2H5 plus times the concentration of OH minus, so the concentration of products raised to their mole ratio, again, it's a 1:1 ratio, divided by the concentration of reactant. So we're going to omit the water, and so my reactant is N2H4. Now, remember, these concentrations have to be at equilibrium because this is an equilibrium constant, okay? So Kb is given to me in the question. It's 1.7 times 10 to the negative 6. So that's a small number. That means you're going to have mostly reactant at equilibrium. Now, my N2H5 and my OH minus, they're both x, okay, at equilibrium. So my numerator will become x squared. And the denominator, my reactant, it'll just be 0.100 m. Remember, I'm using my approximation rule to simplify my math. So if I do a little bit of simple algebra, I'm going to move the denominator up. I'm going to multiply these by each other. And then I'm going to take the square root of... So let me just do all of the math in one step. X will equal 0.000412 moles per liter. And the X value is your hydroxide concentration. Okay, so don't forget that this is this. It's also your conjugate acid, but we don't need to know that to solve this question. We just need to know the OH. So now that I know how much hydroxide I have at equilibrium, let's solve for the pOH. pOH equals the negative log of the OH concentration. So that will be the negative log of 0.000412 m, and that will give me a pOH of 3.38. I'll write down pOH here so we remember what we're doing. So that's great. Let's convert one more step by turning this into pH using this expression. I know that pH plus pOH equals 14, so if I just rearrange that equation, the pH will equal 14 minus pOH. So the pH in this case will equal 14 minus 3.38, and that will give me a pH value of 10.62. Okay, and that should make sense. It is a base, and we see that the pH reflects that, right? Bases have a pH of 8 to 14. So a 0.100 mole per liter solution of N2H4 will have a pH value of 10.62. If you have any questions about this concept, please let me know in the comment section, and it would be so great if you could like and subscribe. Thank you so much for watching, and have a great day.